So let's do a little warm-up question. Let's see if you guys can remember how to do this. By the way, your tests are graded. It is online. So feel free to take a look.
Everyone else they ask questions, but you can only hear the answers.
Well, there you go.
Okay.
Says the diagram above illustrates a nuclear reaction in which uranium-238 emits an alpha particle. How many protons and neutrons will the daughter nucleus have? So how are we supposed to, daughter nucleus is the one that's created. So if we were to write this out, we would have U-238, 92. It emits an alpha particle, which would be 4,2He, plus something else. So I'm going to go on a limb and say 234 and 90. And if you look on your periodic table, what is that? Thorium. So how many protons and how many neutrons will that new nucleus have? Well, we have 90 protons and 144 neutrons. There's only one that tells us we have 90 protons. 234 minus 90 equals 144. Does everybody remember how to do that? Because you will have to do that again on your exam. I mean, we just took the test on it yesterday, so hopefully it's still fresher in your memory than it should be. That's
My brain just doesn't like sweeps everything.
Exactly. I need people just like new information.
well, we are doing we're going to start talking about electromagnetic radiation, and this is actually the lab we do is the one lab that Miss Dreiling remembers from high school chemistry. So this is the one thing that she remembers. Well, I shouldn't say that she remembers. It's the one thing she remembers doing. So, and this went right along with your homework. So we have to talk about the property of waves. Who remembers what the 3 parts of a wave are? Go ahead, Zach. What you got?
You have the trough,
No.
the trout.
No.
The trough.
No.
It's a slope.
What are the properties? Yeah, go ahead. What do you have?
Wavelength, frequency, and speed.
And amplitude is the other one. So we're going to do, the first one we're going to talk about, it's trough.
I told you the trough.
Yeah.
Yep.
Yes.
Yep. I did not do this.
Whose workbook?
You're not alone.
Frequency is the first one. Wavelength is the second. And the third thing is amplitude. The frequency, if I asked you, with what frequency do you go to the store? What am I asking you really?
How often?
How often? That's exactly what frequency is. It's how often a wave goes by a certain point. So we say the number of waves per second. So the frequency is how often a wave passes. Often a wave goes by. The wavelength is the distance between corresponding points in a wave. And this distance between corresponding points in a wave, it can be either crest to crest, which is the top, just like the crest of a wave in the ocean, or it could be trough to trough. It's called a trough because if you look at it, this is a trough right here. If you look at it, it almost looks like, you know, what an animal eats out of in a barnyard is called a trough. It's a giant container that holds it in.
Crest.
crest, and a trough. So the top of it would, right here, this would be, the top is the crest. So if I had to look at it right here, this part here would be the crest about wavelengths. So the top of it, if the top is the crest, so from this point to this point, from the top of one crest to the top of the next crest, that's your wavelength. And Kendall, I'm not going to slow down much because this is supposed to be almost review because you guys had homework on it. Okay. I know you're not. All right. Now on the bottom here, look, I have here to here. Again, that's from trough to trough. So this part here is a trough. The trough is the bottom of the wave. And from one trough to the next trough, that's also how we could measure wavelength. So how many wavelengths do you have in this picture total?
3. Well, almost 3.
Nope. Nope.
1.
1.5. Because look, it's either from crest to crest, that's one wave.
Is a crest and a trough the same thing?
No, a trough is at the bottom.
That's
So this is the trough. That's why that's labeled trough. Yes. We said because when animals eat out of a trough, it's like a almost like a bathtub that kind of looks like a bathtub kind of thing. It can hold stuff in. So that's the trough. So we have like 1.5.
So we count either one, but we don't.
You don't count both. Either one, not both. Because really, when I start this one here, if I'm counting the crest, that's only half a wavelength, right? So it's either crest to crest or trough to trough. And then finally, we have amplitude. Amplitude is going to be the size of the wave peak, how high up it goes. So this is how high it goes, how high the peak is. So if we go back to our little picture here, this right here, from here to here, that's going to be my amplitude.
We're gonna have to draw this diagram.
Oh yeah, you'll have to draw the diagram.
Okay. We're gonna add stuff to it, right? Probably.
No.
Oh, really?
So that's great and all, but how are we going to use that in chemistry? Well, you know the language of chemistry is math. So the way we do that is we have a mathematical relationship where C is equal to, who remembers what C is? Speed of light. Kaylin, honey, are you going to take notes? Okay.
How would you draw that little thing?
I'm going to show you. It's called lambda. Lambda, and some people just refer to it as a TP. And the lambda is wavelength. What do you think the SI unit for wavelength is going to be?
Yeah, is there a B in
No,
Are you sure?
might be.
Do it.
Sorry, huh?
Hertz.
No.
Uh,
Wave, what's the second part of the word?
wavelength.
Length. So what do you think the SI unit's going to be?
Is it greater?
Meters, yes.
Yeah.
There's a B.
LA lambda.
Oh, versus with electricity.
Weird.
Oh.
Wait, the M?
All right.
Wait, what is that?
Meters, that's the SI unit for it. And F is frequency. You're also going to see frequency given as this fancy V.
What?
And now, Zach, what's frequency given in? Hertz. So hertz is actually written like this, or you could write it as seconds to the -1, because remember, frequency is how many waves per second. So really what it is saying 1 over seconds. Bless you.
So we can't spell it out like hertz, like the car.
No. So when you know these SI units, I know that C equals lambda, and that's how I make mine.
Is it okay if I've been doing it like the opposite of the frequency? Then I like that.
As long as I can tell. So, yes,
With the speed of light,
meters per second.
but like last time you said.
It was meters per second. I was doing a different
Oh,
calculation.
okay.
Sorry. Yes. So if you look at this, if this is in meters, and this one here is in 1/seconds, when meters times 1/seconds come together, what unit will they make? Meters per second. What is what? C equals lambda V. That's I remember I said that the V is also for the F. So you can use your units to actually figure out how to do the equation. So that means tonight for homework, you're going to have some plug and chug to do. Sorry, guys. So what does that mean? Well, we say frequency. If you look here, this one has a long wavelength and a low frequency, and this one has a short wavelength and a high frequency. So they're inversely proportional. Very good. So frequency is inversely proportional to wavelength. So what does that mean that it's inversely proportional? Well, as wavelength increases, your frequency decreases. If frequency increases, then wavelength decreases. And Sloan, just like from the homework, the speed of the wave is always constant at 3.0 times 10 to the 8th meters per second.
Oh, yes, same as the light.
Same as the speed of light, absolutely.
So the speed of the wave never changes.
Speed of the wave never changes. So that's always going to be constant. So you know that if I give you mathematical equations, you're either going to be looking for, you're always going to be using, even if they don't tell you. They might say that the speed, that a wavelength has a frequency of 45 hertz. What's the wavelength? And you know that you always use 3.0 times 10 to the 8th meters per second, and then you're just solving for wavelength. That's a constant. It's on your homework. It's it's fairly simple. It's just that easy.
What's the sig figs for that? 32?
This, no, there's no sig figs for this because this is a constant. This like 2.54 centimeters equals 1 inch. It's a conversion. There's no sig figs for that. That's infinite. Forever and ever and ever and ever. So this leads us to this idea, the particle nature of light. So wave nature could not explain all the observations that Planck and Einstein were having. And he came up with something called the photoelectric effect. And the photoelectric effect, did you guys read about it last night? Fantastic.
I haven't read of it, but I know that.
What's the photoelectric effect, Jenny?
It's as the light also have property of of particle, so I have a small like particle called photon, and this energy contains in photon, and once as the light is like to go up like this energy level for an atom, so when the energy level goes up really like high, and then all the like electron is like jump out of that like atom, and it will cause like electron basically.
Yeah. So when light strikes a metal, the electrons are ejected when it hits it. Yeah, when it hits it. And that gives us this thing called the atomic line spectra. So let's take a look at what the photoelectric effect is.
Could light be like lightning?
Light could be anything that gives off light. We'll come back to it.
Does lightning give off light?
You tell me. Can you?
It looks like whenever you write on it,
so.
doesn't it look like she just accidentally has some smudges on the board? Like it doesn't look like it's. Oh, okay. Lonnie, no.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light
Bless you.
pitched on a metal,
Bless you.
and the energy of the
Bless you.
photoelectrons emitted are shown on the meter at right.
Your soul.
If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons
Watch.
emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows
You see how the multimeter is
photoelectrons
moving?
emitted at the highest energy.
It's measuring
So here's an
energy
example of the photoelectric effect.
through electricity, the passage of electrons.
Thanks, Lonnie, for that great demonstration.
Is it like different uses?
What?
Like, are we gonna learn about that?
That's ugly.
That's expected you to know what electricity is.
I know what electricity is, I don't know how he's measuring it.
Through the passes of electrons, it's a multimeter. It measures electricity.
Multimeter?
Yeah.
I don't know, yeah, I don't know what that is.
It measures electricity. So you know that for you guys with the atomic line spectra, when elements are heated, they emit a certain unique set of frequencies of visible and non-visible light. Have you heard of visible and non-visible light before? Visible light. Do you know the colors of the visible light spectrum?
Yeah, Reggie Bid.
Roy G. Biv. Boom.
I'm an artist.
Roy G. Biv.
Do you know that Zach made a joke the other day, and then after he goes, cha-cha-ching, and I'm like, can you believe? I'm like, no.
That's a good joke.
I almost threw up. I was like, no.
How like the worst thing to do in a paper is try to be funny, but then you're not actually funny, and it's like how when you make a joke and like nobody laughs. I said I always laugh at my joke, so I don't know what you're.
So let's look a little more deeply at the photoelectric effect. Cha-cha-ching.
Oh, don't make this thing.
So the photoelectric effect, there is a minimum frequency. What's frequency?
How fast?
Not how fast,
How often?
how often. So there's a minimum frequency needed to, often. How fast is it going is speed. Yeah. The minimum frequency to eject the electron. And that's just a definition. So as the beam of light comes in, it's going to strike the metal, and an electron that was embedded in the surface is now going to be given off.
There's a minimum frequency to reject.
So how often it has to go by?
And like when? the
Frequency of light.
It's the frequency of light.
Deal with this for MEH. This is what happens. And then Mr. Ryan's just like, haha, and I'm like, Mr. Ryan. Deal with this.
You're like Mr. I don't encourage this behavior.
So let's list out the electromagnetic spectrum, or the EMS. Now it's in your book, and I know that you guys all looked at it last night. I don't remember what chapter it is off the top of my head. Is it 11?
Yeah.
Okay.
Sure.
My favorite thing from last night was that bird. The bird with like the different things, and it had to do with like mating.
Oh, the parrot.
Yeah.
So,
I'm sorry.
what electricity was it measuring?
Yeah, I'm just
It was measuring the frequency of the light.
But, like, where was he measuring it from? Like, what
From
was that
where-
thing connected to?
It was connected.
To the thing of metal that was having
Yes.
light in it?
Yes.
So metal emits electricity when light hits it.
Electrons. It can, yeah, depending
so,
on.
like, right now,
Right now, it's emitting electrons. It's not going to shock you, though.
emitting electrons doesn't mean it's losing mass. Like when we say emitting electrons, what do we mean?
It's not losing mass. Electrons don't have mass.
Trying to grasp
I know, but I'm saying
the
electrons don't have mass.
It's gonna grow a tiny mustache.
Because I can't understand anything.
There's nothing really to understand about it. It's just kind of more of a memorization thing.
I'm not good at that. That's why I'm
Sorry.
excited by it. I have to know what I'm talking about.
Let's go ahead and look at our shortest wavelengths. So starting with your shortest wavelengths, you're going to have, I'm sorry, not shortest, longest, AM radio waves. You remember that? What comes after AM radio waves? No, it's actually shortwave. Like a shortwave radio. It's literally between AM and FM. Then you have TV waves. So TV radiation, as in television.
What are we talking about?
You're talking about waves of energy that everything emits. If you see, I don't understand how you can't
No, I get it.
grasp this. Do you know that right now out in space, getting further and further away from us is the first radio transmission? The first radio transmission, it was heard on a radio, it came out of the speakers, and the energy from that transmission is still being heard traveling all the way out in space in the form of a wave. And it's continuing to get further and further and further away from the source. You could calculate how far away it is based on the equation that we know, speed of light and the length of the frequency. You can do that. But that's what we're talking about. So like radio wave, AM radio waves, their waves are really, really long. If they're there are different types of waves. So they're really, really long. If they're really long, that means that they have really low energy. So it doesn't take much. Then you've got shortwave radio waves. Then it's TV waves. So the first TV transition or transmission. AM is the longest wave, lowest energy. Longest wave, lowest energy.
Like in the morning when I can't get out of bed.
That would be your AM. That would be your AM wave. Yes. Then you have FM waves, FM radio waves. What?
How do they control where the waves are like centralized? Like, let's say if
You have a big old radio tower that has the big dish on it, and it focuses it, almost like how your ear is designed to focus sound waves into it.
Right.
Then the giant dish
so
is
there's, like,
focused.
a radio channel just for Chicago.
Yeah, there are radio channels just for Chicago.
No, I know there are, but like the dish just focuses.
It's focusing, yeah, its wavelength is such that you get the strongest signal in a given area.
That's why when you like drive
Please tell me you
outside,
didn't
when you
know.
try to go
There's
on like
national
102.5 in Michigan, it gets all
And national stations don't have a restriction on where their wavelengths can go.
Yeah, they're continuing bouncing off of other towers.
Zach, do you think that everywhere was able to get Chicago?
Yeah. Everyone has the capability.
You have
Sometimes just that outside.
radar waves. After radar waves is my favorite. Microwaves. This is the radiation that's going to kill you. JK. Then you have something that we're going to
Maybe some mac and cheese.
Popcorn with the door open.
Infrared waves. So infrared, and you're going to see infrared written as IR all the time.
Is that really how infrared is spelled?
Yes. So this is long wave, low energy. And remember, our wavelengths are going to be measured usually in meters or some sort of meters or usually nanometers. And our energy could be anything. Usually it's in, what was the measure of energy? I don't remember. Not calories. Joules, very good. So if I go through that, you know what comes after infrared?
What was in parentheses for the lower?
Joules. I said because energy is in joules. Then you run into what we're going to call the visible light spectrum. The visible light spectrum runs in order from red, orange,
Is this all talking about the same?
yellow, yes,
Like still wavelength?
yep, green, blue, ooh, indigo. I'm going to try and find something indigo-y. Indigo and violet.
I would say race more, but they kind of forgot.
So we've got...
How to spell.
Raise more except for the first three.
So we have our visible light spectrum comes next. And remember, we're going from the longest wavelengths to the shortest wavelength. Notice that infrared is right before the color red. So that's a great way to remember the order, is that infrared has longer wavelengths and less energy than red does in the visible light spectrum. What comes after violet? Ultraviolet.
Just kidding.
I should know this. There's like an optics course somewhere.
Ultraviolet does. Or UV. Do you know what comes after UV light?
Mega ultraviolet.
Nope, it's something that's going to be traveling even faster. It's so strong that I can use it to see through you.
Oh, X-rays.
X-rays.
Blue and indigo.
Uh-huh. So then it's X-rays. And then finally, what's the fastest, most powerful ray you know?
I know, gamma rays.
Gamma rays.
Can I please be dismissed from
Fast like that.
Can I please be dismissed?
You did not just do a fake it power riff.
So yes, you have to know the order of the visible of this. You have to know the order of the visible light spectrum.
We can learn it.
Wait, are they all visible then?
Only visible light spectrum, only the colors is the one that's visible. Everything else is the whole electromagnetic spectrum, going from the longest wavelengths,
Yeah, I mean, is that all visible?
red, orange, yellow, green, blue, indigo, and violet, the ones that say VLS, the colors, yeah, that's the only thing that's visible.
What's in the parentheses?
So what's, wait,
For what?
meters?
Meters or nanometers? What's up?
What is
Visible light spectrum.
Oh,
Visible light spectrum, that's what you can see.
okay.
What is the color of gamma?
It has no color. That's what I'm saying. There, you can't see those. It has no color.
You can only see the
This is-
in the
What's
triangle.
on the left side?
You can only see what is underneath VLS. Stands for visible.
Red, orange, yellow, green, indigo,
You know what the word visible means, Jenny?
Yes.
Okay, visible light spectrum. You can only see things in the visible light spectrum. Which things are in the visible light spectrum? Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Those are the only things you can see. You can't see ultraviolet radiation. You can see the effects of it, but you can't see it. You can't see X-rays. You can see the effects of X-ray on a film, but you can't see it. You can't see gamma rays. You can see the effects of gamma rays after a nuclear fallout. So what does this mean? Well, it means that everything is constantly, yeah, it's like John Cena. It's like everything is constantly has this light bouncing off of it For example, Jenny's shirt. What color or what frequency of light is Jenny's shirt?
It absorbs everything.
It absorbs everything, all those other ones, but it's giving off the electrons in the same frequency as the color red. That's why we see it as red. What about Helios? His shirt is black. Which one is he giving off?
Nothing.
Nothing. Very good. Black is absorbs all color, or it gives off nothing. What about white light? Gives off everything. That's why it appears white. So remember, black absorbs everything, gives off nothing.
We should do an experiment where we take
So
all the
this all
colors
affects
and
how
mix
we
them
see
together.
the color.
This is how we see the color. It's based on the wavelength of energy.
Alright. So is that why people see different colors?
But it also can be about how their rods and their cones work. Yeah. Yes.
So black is absorb everything and give off nothing. So it's just like they don't reflect.
It doesn't reflect. Yes. It's being absorbed. If it's not reflected, it's absorbed.
Yeah.
Okay.
There's a remix.
So this gives us the photoelectric effect is only going to be explained by this idea of, like, and Jenny already called it, by these energy packets. These little packets of energy in the form of light called a quantum. Now, I like to think of it as, if you could think of opening a little Splenda packet, and instead of being delicious little sugars in there, it was just light that came out. And that would be a quantum. Okay? Yeah, when you open it, you'd have that. That's a quantum. It's a discrete little packet of light energy.
Solace.
So a quantum is the minimum amount of energy that can be gained or lost by an atom. And this gives us our photons, and photons are massless particles. No, they're not. This says photons. We already said that photons are discrete packets of light. Photons, they're massless particles of light of a certain quantum or amount of energy. So you go back to this idea of the Splenda packet, and you pull open your Splenda packet, and inside there, this little bit of light comes out. So if you have a very large quantum, it's a large amount of energy, it's a really bright light. If you have a little bit, then it would be less bright. But it's a small packet of energy. They call it a discrete unit is what a quantum is. It's a discrete unit. It's just like, how much is in a dozen? 12. Well, how much is in a quantum? It's a certain amount. It's different for each thing because it's the minimum amount that it takes for that atom to gain or lose energy.
Is
Yes.
it always white light?
No, not necessarily. We can split the. It's going to be based on what energy they give off.
Right.
So it's
Do you
different
have
for every atom.
blue Splenda packets, like the pink ones?
Those aren't Splenda, honey.
Different for every atom.
Yes, it's different for every atom.
Oh, there's E-type.
Yeah, that's equal Splenda and sweet and low.
I only use actual sugar. Like what's the K-pop group?
Says the diabetic.
Oh.
All right, so the equation, so we've already gotten one equation today. Do you remember the first equation? C equals lambda V or C equals lambda F, and that's going to help us find our wavelength, which is the area from crest to crest or trough to trough, or our frequency, which is how often a wave goes by. This one's going to let us calculate the energy. And its energy is by this equation here. So E equals HF, where E is the energy. What's the unit for energy? In joules. H is something called Planck's constant, and I'm going to give you that in a minute. And F, what did we say F was before? Frequency. And you're going to see it again as either F or V. So it could be written as H, funny V. So Planck's constant, and yes, you have to know this, and you will after doing your homework, is 6.6 6.26 times 10 to the negative 34th joules per second. Yes. 6.626 times 10 to the negative 34 joules per second. And that's Planck's constant. Planck's constant, not Planck's constant.
I know, I didn't finish my K.
So unlike our other one where it was as wavelength increases, what happens to frequency in our other one? Decreases. They were inversely proportional. In this one, as frequency increases, in this equation, E equals HF, energy increases. So the relationship between frequency and energy is what? So this is directly proportional. I'm sorry? The relationship between frequency and energy is directly proportional. So let's see if we can't do a practice one.
For which equation?
We're going to do both of them. Let's do... So let's do a practice one here. I have to make sure it's not on your... Okay, it says the wavelength of green light. Can you see green light?
Yeah.
Very good. The wavelength of green light is about 522 nanometers. What is the frequency and energy? Yeah. All right, so what's the first thing I need to do? Huh? I have to write the equation. It asked me for two things. It asked me for frequency and energy. I've been given a wavelength. So what equation am I going to use to find the frequency? I can't do that because I'm looking for energy and I don't know the frequency. So I have to use C equals lambda F or lambda V, whatever you want. Because in this case, I know C. What is C? 3.0 times 10 to the 8th meters per second. Very good, Zach. He said, but wait, my wavelength is given in nanometers. What do I need to do? Convert it to meters. How do I convert that to meters?
1 nanometer is what?
I know that
10 to the negative 12? No, negative 9.
nanometer is -9. So I know that 1, or I can do 1 times 10 to the -9 nanometers, or 1 times 10 to the 9, sorry, nanometers, is equal to 1 meter. So go ahead and convert it, because my nanometers will cancel out and I'll be left with meters. So 5, what do you end up with? 5.22 times 10 to the
5.22 times 10 to the negative. We get a parenthesis?
I'm waiting for confirmation.
No, I just don't know if I forgot a parenthesis.
I'm gonna
Redo it.
beat you
What do you, why?
because you use that caret.
The 10?
Yeah.
I didn't use the caret. That's what happens if you press times 10 to the something.
You're not supposed to.
I
You're
know
supposed
you
to.
can do E, but it's
You're
the
supposed to
same
use
thing.
E.
You and Han told me it was the same thing.
I got 5.
Remember that 10 button? Like the times 10 to the whatever, or the E button?
I got
Timing calculator.
5.22
Aren't they the same?
Times 10 to the -7. Yes.
Aren't they the same?
They are, but you are not careful enough to use it. He is.
Wait, so then what happened?
That was the bell. Let me give you your homework. So then you should be able to solve for
I had
frequency.
it right. What do you mean I'm not careful enough to use? I had the right answer.
This time you were careful. Not bogus. You need a regular calculator for my class.
I actually, I found a really good app that actually lets you like graph and everything, and it's free. It's not bad.
No, it is not milk. It's starch. They're doing a spit lab in biology.
Oh, I hate that lab.
Oh,
I
yeah.
hate that lab. I hate that lab.
You get to see your cheek cells.
No, not that one. This is the one where they spit in the cup,
Ew, that was so gross.
and then you have to put it in the test tubes, and it's warm. Hey guys, I will be here early. I will be here after school. No work, no credit, and sig figs count, Helios.
But Pep comes in the car.
Oh, you're doing the fun lab today.
I'll be back.
I'll be here if you need help. Sig figs count, no work, no credit. So you're gonna have to do your work on a separate sheet of paper.
Okay.
Yeah.
Did the vial that does the tongue
No, I think you
paper?
should go.
Oh, that's when we get to
I know,
genetics.
that's what
Yeah.
you- yeah.
It's terrible. You like test to see if you have
You said- okay, well, let's do it.
Why are you using a piece of paper?
You okay?
Yeah.
It's PTC paper.
Great.
Bye, Jenny. Thanks.
Counter-
We're on time.
I did it.
It's so nice. It's not milk though.
Oh, but you guys are doing a spit lab, so that's fun.
Make sure you go on your Instagram.
Yeah, exactly.
Well, it's not really, but
No.
they're comfortable.
Haley, I like your sweater.
Thank you.
Oh, that hurt.
Hi, Connor.
I'm okay
Did
with
you say hi, Connor?
I did,
I
Connor.
thought that was flowing.
Like, I'm gonna get rid of this one.
I turned around.
I can throw my voice. Fool your friends. JK, you're late, Ryan. Does suck. 'Cause she pays attention.
Oh my God, no, yeah, that's why right when we started practicing, I was like, I gotta lift all my arms up. And it's not the lifting my arms up, it's the part, but like that costume. I have to hold them. Yeah, I was like, I literally just have to hold them the whole time. So I have to keep my, like, it's just like this, the whole entire time. I'm like, why? Why does it have to be this complicated?
So apparently I started writing my name on some stuff and I always forgot to put, I wrote FR and stopped writing.